So next up, we are going to explain the vector equation of a plane in scalar product form. So we know that there are actually three ways to explain the equation of a plane. The first two being the vector equation in parametric form, vector equation in scalar product form, and thirdly is to express it in a Cartesian form. Alright, so vector equation of a plane in scalar product form. Okay, you realize that here, okay, what we're going to do is we just have to first define a point that lies on the plane. Let's say I call this point A. Alright, so this is a point A. Again, it would be the point and with maybe position vector, okay, A, and on top of that we can list another vector here, maybe n, and this n will be a normal vector. Okay, so n is a normal vector. Alright, it need not be a unit vector, it's a normal vector to the plane P. Alright, and over here, right, okay, what we can do is now from here, how do we so-called identify or list out any general point on the plane? So let's say just quickly, if we were to consider any point on the plane, okay, maybe just call it R. Alright, let's write maybe R. Okay, maybe R can be any point on the plane. Again, yellow. Alright, and similarly, R can be it can be this way, and R over here, right, point R, okay, let's just give it the coordinates, maybe x, y, z, right, and we can see that since AR, right, it lies on P, right, we can also assume that AR, if we consider the vector AR, right, can we say that it's perpendicular to n, right? We can say it's perpendicular to n, right? And from here, right, since it's perpendicular to n, right, the next thing we can do is we can also assume that AR dot product with n, right, will give us 0 since they are perpendicular, right? And how do we express AR? Now we know that we can simply write AR as OR minus OA, right? So this is AR at the side. This is just OR minus OA. Okay, so the direction vector of OR is R here, OA is A, right? So very simply, this is just R minus A dot product with n, which will give us 0. And this also means that, being a dot product, we can actually distribute it. It's a distributive. A dot n equals to 0. And this also means that R dot n is equals to A dot n. Alright. So this is actually this scalar product A dot n, right? It gives us a constant. So what we do is, we just take A, and A can be any position vector, because it need not be, even though it's here, right, our normal vector can be anywhere. So I can easily start this whole explanation all over again by putting a normal vector here, and then your A also can be here. I can put a normal vector there, and A also can be there. But generally, right, okay, A must be a position vector. This must be a position vector on the plane. Okay, and on top of that, this has to be n has to be a normal vector to the plane. Okay, with that, right, very quickly we obtain this equation where R dot n equals to A dot n, and we can actually assume that this gives us a constant D. Right? So thus we have the vector equation of plane P to be equals R dot n equals to D, where D is equals to A dot n, and it actually is a constant. So there's no actual meaning to this geometrical meaning to see. Basically, this D, right, is the dot product of any position vector on the plane together with n.